I'll go ahead and share my screen. And begin the slideshow. All right, so first I'll start with a quick introduction of myself. So my name is Rushil Kapadia. I'm a Regent scholar pursuing a bachelor's in science for electrical engineering and computer science at UC Berkeley. I'll be graduating this semester. My areas of research include AI and ML and also the blockchain space. I've experienced working closely with high school students through tutoring, teaching this class before, and other such classes. So the agenda for today is we're going to start off with just going over what machine learning is. And then we're going to touch on some machine learning basic concepts, some use cases, and then I'm going to tell you guys about a few careers and majors you can go into with machine learning. And then lastly, I'll end with a demo that was given by one of my mentees for a science fair project that he created. And we'll end with a little bit of information about the Eldridge Academy class. So let's begin with what is machine learning. So machine learning is a method of data analysis based on finding patterns in data and making decisions based on those patterns. It's a branch of AI that seeks to replicate human behavior through data. So if we try to come up with an example, we might be able to come up with an example about weather. For example, perhaps I want to figure out if on any given day it's going to be sunny or not. So maybe I look out today and I say, I see the sun out, I don't see many clouds, it doesn't look like it's going to rain, so I think it's going to be sunny today. That's a prediction that I'm making on patterns and data. So a question for everyone here, what are other factors that you could look at to decide whether or not it's sunny? If you have any ideas, go ahead and drop them in the chat. Something maybe that a machine or something else could use to learn whether or not it's going to be sunny or it's going to be raining. So yeah, feel free to put any answers in the chat. So another example might just be the presence of clouds. So that's like a true or false, right? So if there are clouds, it's less likely to be sunny. If there are not clouds, it's, if there are clouds, it's more likely to rain and less likely to be sunny, and vice versa. All right, we can move on. So yeah, so believe it or not, machine learning has actually been around for quite a while, for about 20 to 25 years. So why is machine learning becoming so big all of a sudden? Well, the reason is threefold. Firstly, big data. Machine learning requires a lot of data, and that's something that's only now possible with the recent web scale. Furthermore, there have been major computing advances in recent years, and ML requires fast computers, dedicated processors that are really only available in the last 5 years. And I can speak from experience. Running even simple things on my personal computer can take up to a few hours to a few days to run. So it really requires fast processors and better computers that have only come in recent years. Lastly, there have also been some mathematical advances that have led to more complex machine learning models that we'll go ahead and mention later. That have made more complex compute possible. So what is machine learning? So simply put, we can describe it as a function f, where we're trying to take in some input and return a desired output. So if you look at that image on the bottom right, you see that we take an image of a dog and we classify. So classify is like we label it, or we like say that this is a dog. And in the second example, we take in an image of a cat and we say this is a cat. So that's our goal here. And for many theoretical cases, we can choose a function that does exactly this. So what that means is if I give any picture of any dog, it should be able to say this is a dog. Any picture of any cat, it should say this is a cat. And maybe even some humans for some problems can reach this state, but you can envision that maybe there's a dog that looks like a cat or a cat that looks like a dog, and even humans get that wrong. So similarly, in real life, we generally can only approximate this function. With like a pretty good approximation. And the reason is, similar to humans, there's some images that are very complicated. Maybe there's all signs point to like it being a cat, like the dog has pointy ears, the dog has eyes that looks like a cat's eyes, but is in fact a dog. or just some cases are too complicated and it's too hard to use the information presented to make a decision. So now we're going to go ahead and take a little bit of a look into the math behind ML. So we're going to start off with something called linear regression, which in a way is kind of the base machine learning example. So what is linear regression? Well, if you think all the way back to maybe your first algebra classes, you might remember the equation y equals mx plus b. Now, y equals mx plus b is basically you take some input x, right? You multiply it by m, which is known as the slope sometimes. You add some other number b. M and b are some given numbers, some constants, which is like the y-intercept. And then you get your output y. So this example that we give below is for the x-axis, we say that perhaps it's the age of a customer coming into our store that we have. And y is the number of hours that they spend in the store. So what we're trying to do here is come up with some correlation or some relationship between the age of a customer and the number of hours they spend. So as humans, if we look at this, we can get a pretty good idea of what type of line we need, right? If we look at the low ages in this case, they're not spending much time. If we look at people at higher ages, they're spending a lot of time. And the relation seems to be something what we call linear, which means we can draw a line right through it to model the data pretty well. So what we do to get here is we guess some sort of m, maybe we say m is like 2 or 3, and we guess some sort of b, which is maybe like a very small number here because the y-intercept's low, and we create a line that fits this data. However, our goal here is not to have some human guess random m's and b's and see if a line fits data. We want to have a machine learn these values. M and B, we want them to learn what they are so that we can go ahead and have machines actually create good fits for data. So now we're going to go ahead and look at ways to actually make that possible. So the first thing we need is a function to learn a loss function. So basically what that means is when I was saying a human is sitting there choosing M and B values, right, to fit the data, they know whether the line fits the data well, right? And generally to them, it's because they're like, oh, the dots are pretty close to the line. The machine needs some way to know whether or not the line, the M and B values it chooses is good or not. And for that, we create an optimization problem. Now this sounds like a fancy term, but I promise you that all of you have solved a optimization problem before. A simple example is buying the cheapest and highest quality phone possible. So when everyone goes to buy a new phone, they're always looking for the highest value for the best cost, right? And that's an optimization problem already. So what we can do is we can define a loss function to guide that algorithm on the parameters that matter. So let's say we choose 2 parameters. So instead of M and B here, we're choosing the cost of a phone and the rating of a phone, right? So we might create a naive loss function, which is the cost of the phone minus the rating of the phone. So if we go over and look at equation 1 on the right, we go ahead and see how this works. So phone A costs $100. We gave it 5 out of 5 stars, or it's given 5 out of 5 stars. So we say 100 minus 5 gives us a 95 value. Phone B is $60, 0 out of 5 stars. So 60 minus 0 has a value of 60. Now, the problem here is actually that our value is defined by the lower the value, the better the phone. It's a loss function, and we want to get minimal loss. So the lower the value, the better it is for us. And the problem here with our naive function is that phone B was valued better than phone A. And we consider this a problem because we don't want a phone that's 0 out of 5 stars. Even if it's $40 cheaper, it's probably not worth it for us. So instead, we go ahead and consider a better loss function. And to do that, we now need to think, well, the star value matters a lot more to us than perhaps the monetary amount, right? We're willing to pay $40 more to get 5 more stars. So now what we can do is we can do the cost of the phone minus 10 times the rating of the phone. Now, if we redo the math that we did before, 100 minus 10 times 5 gives us 50. 60 minus 10 times 0 still just gives us 60. So now phone A gives us a better value since it's lower. Remember, lower is better. So now we've created a loss function. But again, here's another problem. We can't just figure out what's the lowest value. For a lot of these basic functions, like maybe like linear regression for just two variables, perhaps there are equations that actually can solve these loss functions immediately. So you just need to plug it into the equation and get to it. But the problem is when we start getting to more complicated examples, when we start getting to multiple dimensions, where it's no longer just two variables we're considering, but maybe three variables, maybe four variables. So in those cases, we no longer can just solve a simple equation to solve our optimization problem. And we need to find better ways to approximate that. So the next step of what we do is called gradient descent. Gradient descent is basically something that helps us find these minimums, right, of the loss function. So if you look at the equations at the bottom, those are some equations of how a loss function might look like as a graph. So on the right, you see a simple, just what's called a parabola, right? And you can clearly see that the global minimum cost, right, is right there in that middle, when you reach that like bottom piece. So what gradient descent basically does, without going too much into the math, is it's like placing a dot randomly on this graph and then letting it drop and letting gravity move it every time step. So you see each of these arrows is basically a movement per time step because of, say, gravity. And eventually, if you imagine, while it might oscillate, all right, like move left and right at the bottom for a bit, it's eventually going to go and sit in that middle of that graph. So that's what we want. And it's going to go ahead and find that minimum. Now, unfortunately, most cases are not going to look like this on the right. Again, and as I mentioned, if it does look like the equation on the right, there are probably simpler ways of solving it than gradient descent. What we end up usually ending up with is that graph on the left, where you can see multiple 3D hills and ravines and stuff. And gradient descent is generally pretty good for approximating minimums in these types of landscapes. In reality, gradient descent requires multivariable calculus, but for our intents and purposes, we can just abstract that away and think of it as a ball rolling down hills and finding minimums. So those are the two base ideas needed to actually set up machine learning. Now, the only problem right now is in our linear regression example, using M and B is sometimes not enough. Our data is sometimes non-linear and also uses more dimensions than just two dimensions. So we can't just use one M and one B. We might need a lot of M's and a lot of B's. So to go ahead and build something called neural networks, which is what's used most commonly now in machine learning, people actually went and looked at human neurons to get inspiration, hence the name neural networks. So without going into too much detail, if you go ahead and look at this neuron at the bottom, you go ahead and you can see that at the dendrites on the left side of this neuron, we go ahead and take inputs, right? X1, X2, all the way down to Xn. It goes down, in this middle process, it finds some important information about all these X's. And then it goes ahead and based on that information, gives out all these Ys, Y1, Y2 to Ym, which are these outputs from the axon terminal. So in a way, we're actually going to do the exact same process in our neural networks. We're going to take in inputs, X1 to Xn. We're going to do some work in the middle, find some important information, which will go ahead and help us find some outputs, Y1 to Ym. So if you go ahead and look at the bottom right here, you'll go ahead and see what a neural network structure might actually look like. So remember, we mimic human neurons. So we try to learn multiple values about the inputs, and we call those hidden states. So these are kind of like the M's and the B's in the linear regression example, right? Those are just values that we somewhat learn about the information. And we store them in these states called hidden states. We can have multiple hidden states. The example below just shows one. So all these inputs go to all the hidden states. And from the hidden states, we go ahead and produce an output. And to go ahead and actually solve this, as we mentioned before, it's really important to use gradient descent and the loss function. And we use both of them in a process called backpropagation. So just again, to reiterate, backpropagation is just a way for us to apply gradient descent on a loss function in our neural networks. So yet again, it's not that important to understand all this. I'm going to go ahead and talk in the future about like libraries and everything that has all these implemented. All we need to know is on a high level what it's doing. So yeah, let's put all the math together, everything that we kind of talked about. So we start with the most basic machine learning form, linear regression, right? Y equals mx plus b. And we decided we need a way to find what m and b are. So we want to use machine learning to find the best fit line. We don't want to use a predetermined formula, which we generally could get for simple examples, such as linear regression. So what we did is we added a loss function to teach the machine what m and b values are good, right? What determines good, what determines bad. Next, we found gradient descent, which helps us roll a ball to find the minimum m and b values. So again, a machine cannot just know what's a minimum value of a loss function. It needs to find it. And to find it, we roll a ball. And that's gradient descent. Next, we went ahead and took inspiration from human neurons to develop neural networks that could take in multiple inputs. So our problem here so far was one input, one output. Now we found a more robust system, which allows us to take in multiple inputs, multiple outputs. There are many hidden layers in these neural networks, which find some interesting, we don't really know what that is. We'll talk about that later, or maybe like, if you understand it better, you'll understand what interesting is better. But for now, we can just think of it as interesting patterns in the data, which are calibrated through backpropagation. Then we traversed through multiple hidden layers and we got our output. All right. So now we're going to talk about a few categories of machine learning. So now that we've covered all the math, let's take a step back and actually look at use cases and types of machine learning. So what can we use machine learning for, right? One of the biggest, the three biggest ways it's used right now are in these three here. The convolutional neural networks, which are called CNNs, the recurrent neural networks, which are called RNNs, and Q-learning. So CNNs, or convolutional neural networks, are used for something called computer vision or image recognition. So an example of that is that image on the bottom left, right? So you can see that in this image, there's a lot of cars, there's a truck, there's a traffic light, there's someone riding a bicycle, there's a bicycle, and our neural network has actually identified most of them. It's drawing these things called bounding boxes to say, oh, hey, look, that's a car, that's a bicycle. And it's identifying what it is. Now, why is this important? Well, you could think of many cases. In fact, if you look at self-driving cars, having computer vision is very important, right? You want your car to be able to identify traffic lights. You want it to be able to identify other cars. You want it to be able to identify pedestrians, bicyclists, all that. So having a model that can accurately find all this, given an image, is very important. And another cool example, I'm going to go ahead and show it here, is this website called This Person Does Not Exist. So this is an image of a person. And actually, it's not a real person. What that means is this is a computer-generated person. It does not exist at all. This computer has looked at many images of humans and gone on to create its own humans based off that. So if we refresh this every time, it's a human that does not exist. It's all computer generated. So that's really cool stuff. Next, we'll talk about RNNs, or recurrent neural networks. So what these are used for are text translation and NLP. So one really cool example is if you look at this middle image, it's a little bit small, so it might be hard to say, but it says large text that says, welcome to my newsletter, and a blue button that says subscribe, right? So someone typed that in and then click generate. And what it did is it generated some HTML. So what this means is this machine learning algorithm was able to take in a command, like a human command, me saying, can you create a website with a large text and a button underneath it? And was able to actually turn it into HTML. So this could be very interesting for the future of creating websites. There are a lot of other examples of text translation and NLP. I mean, the simple example is like Google Translate, or just translate in general, right? Having machines learn how to translate from one language to another. Or if you have anything like Siri or Alexa, right? Any of those guys use NLP to go ahead and try to respond accurately to questions. Maybe it's never heard before. And yeah, so That's what recurrent neural networks are and their use cases. So the last one I'm going to mention here is Q-learning. So Q-learning is a very interesting type of machine learning. So this one it still uses a lot of the same fundamental math that we've talked about, but it takes a different approach to machine learning. What it does is it tries to mimic humans the best it can. So basically what reinforcement learning does is it uses reinforcement, positive reinforcement, to go ahead and teach the machine what's good and what's not good and what it should do. So the example here is AlphaGo. So AlphaGo played a game called Go. And if you don't know what Go is, it's a strategy game that's similar to chess, but has a lot more possible moves. So what this bot did for AlphaGo is it just played like thousands of millions of games, and it learned by either winning or losing. And every time it won, it learned that was good behavior. Every time it lost, it learned, okay, this is not so good behavior. And over time, it learned what's optimal and what's not optimal by just getting rewards and punishments. So based off the structure, it's able to train itself and get better over time. So yeah, so that was the CSP. So we're going to talk a little bit about the CS behind ML now that we've covered a lot of the math behind ML. So let's start by a few key terms. So there's learning and there's labeling. So learning is basically what we've talked about so far. When you're given some input, you want to learn something about them. You want to find some interesting patterns, something about the data that helps you make predictions about the data. Labeling is what we've been doing so far, which is, when we're given an image of a dog, we want to label it with an image of a dog. When we're given an image of a cat, we learn what a cat is, and then we label it with the name cat. So everything I've talked about so far is mostly called supervised learning. So what that is we take in data that is labeled. So I will give the machine a bunch of images of dogs, and I will give them all labels of a dog and a bunch of images of cats with a label of cat, and tell it to learn the difference between dogs and cats. And reinforcement learning is another style of learning. And again, as I mentioned, the idea here is giving positive reinforcement, giving some rewards, right? So in this example, maybe I'm trying to train a Mario ball, right? And what I do is every time Mario kills an enemy, I give Mario a reward, maybe +5 reward. Every time Mario finishes a level, maybe I give a +10 reward. And maybe for every second that Mario spends finishing the level, I deduct half a point. And over time, Mario's going to try to get as much reward as he can. So he'll try to finish the level as fast as possible, killing as many enemies as possible, and finishing the level. Now, the third type of learning that I haven't really talked about too much, that's actually on the rise right now, is unsupervised learning. So we actually did see an example of this. The This Person Does Not Exist website uses unsupervised learning. So what that is sometimes we can't get these labels, right? These dog and cat labels. So what we do is we give data without labels. For example, I might just give a lot of images of dogs. And I'm not saying that this is a type of dog or anything. Just I'm saying these are all dogs. Learn what a dog is. And what the model will do is instead of labeling stuff, instead of saying, hey, this is a dog, this is a cat, it will say, hey, these are things that make a dog a dog. And based off that, it'll be able to maybe generate new images of dogs, identify new dogs better. And there are a lot of use cases for learning about data without labels. So now the next important thing to talk about is the machine learning project flow. So we've kind of talked about all this stuff about how machine learning works, where you can apply it, but it's really important to understand how to actually go ahead and make machine learning projects. So the first thing you need to do is define a machine learning problem and propose a solution. So I'll talk about this a little bit in the future, but the mentee that I worked with came up with a problem that during quarantine, students were not paying attention on Zoom. And so that's an ML problem. And his solution was maybe if there could be some sort of tracker that could keep tabs on all students and say, hey, they're paying attention, they're not paying attention, and maybe either give this data to a teacher or give some feedback to the student. It could help students pay more attention during class. So the next step after coming up with the problem is constructing a data set. Now, this is a big, big step. All that math, all those steps that I showed previously do not matter if you do not have a good data set. The problem is we can have models that are really good at finding patterns in data. But if there's no patterns in data, right? If there's no patterns to find, or if there's just nothing you can really do with that data, you're not going to get any model that like makes any sense. So you need to have good data and you need to have sufficient data. You need to have enough data. I can't just give 2 pictures of a dog and say, and 2 pictures of a cat and say, hey, differentiate between dogs and cats. That's not enough. So what my student did is he found hundreds of images of Zoom, of students on Zoom, paying attention, not paying attention, and went ahead and kind of got just a database of those. Next, what you do is you choose an algorithm and train a model. So we've talked about all these algorithms, like, CNNs, RNNs, those are models, and you can go ahead and do different things with those models. So you go ahead and create a good model and algorithm, and you train on that. What that means is you run a few steps. You allow your model to like run multiple steps, which are called epochs, and be able to learn. Next, you go ahead and use the model to make predictions. So here you give it new data it's never seen before, right? So the student separated some of his images of students paying attention, students not paying attention, and gave them to the model and asked, are they paying attention? And saw how much of the time the model would get it correct. So like this is kind of accuracy, right? So if it gave 10 images and it classified 8 of them correctly, we have an 80% accuracy. Obviously the numbers would be higher. But at this step is where we go ahead and spend the bulk of our time in machine learning, which is optimizing. So you see the arrow that goes backwards. So the problem here is there's no optimal model. I can't just give you a model for every situation. It's it's kind of a very experimental process. You need to see what works, what doesn't work, because every set of data is very different and reacts kind of differently. So perhaps you went ahead and did all this and got 60% accuracy. So keep in mind, 50% accuracy means for either paying attention or not paying attention, means you're basically just guessing, right? If you guess, if I guess paying attention every time, I'll get 50% accuracy. So getting 60% accuracy is not that great. That means you're barely doing better than just guessing. So what you do is you go back and say, okay, maybe I did not do well on images of people sleeping. So I'm going to go ahead and react to them. I'm going to do something. I'm going to change my model. I'm going to change my data. And based off that, hopefully I'll get better results. So you go ahead and do that. You change your model, you change your hyperparameters, which are kind of these parameters that help kind of tune your model, or you go ahead and fix your data. And based off that, hopefully you'll get better results. So that's kind of the machine learning project flow. So now we're going to go ahead and talk about what software you use for machine learning. So all the math that I've talked about so far is generally abstracted away in all these really, really powerful libraries. So if you use these libraries, you can go ahead and just do machine learning, create loss functions, add in gradient descent with just a single line. So what we use is we first of all use NumPy for data structures and linear algebra. So what that is basically, these matrices, these arrays. Again, we don't need to worry about those. Like the libraries, we'll go ahead and use them later on, but we just need something to go ahead and like represent these in variables. So we use NumPy for that. SciPy is good for images and also just other sorts of linear algebra. So especially when we get to like computer vision or image identification, SciPy can really help us out there. There are 3 major libraries that are used for the actual neural network. So they provide these things, like they provide CNNs, they provide RNNs. So those are Keras, TensorFlow, and PyTorch. Those are all separate libraries, and depending on your use case, you can use one or another, but they're all pretty good. And lastly, use pandas and matplotlib for the data. So they help you arrange your data, visualize your data, and go ahead and work with your data more easily. The most popular language so far for machine learning is Python. So I would recommend using Python, if you want to get into the machine learning space. And one of the most popular platforms is Google Colab. And the reason is it's a nice online editor that lets you use GPU. And GPU is just something that lets you speed up your machine learning process by a lot. It can cut it down from 10 hours to 3 hours. So Colab gives a lot of free GPU, so that's really nice. Yeah, so all that is kind of one way to do machine learning. That's if you want to do machine learning locally, build your own networks. It's more for a personal project, science fairs. If you're building an app, building a proof of concept before you want to go ahead and do anything with it. Um, but in a lot of cases, you might want to use machine learning on the cloud if you're doing a bigger project, right? If you're actually creating a full-scale app that you're publishing, there are a lot of options. There's IBM Watson, there's Amazon Cloud, there's Microsoft Azure, Google has its own cloud as well. All these guys go ahead and give their own stuff to allow you to do machine learning on the cloud to build larger projects. Yeah, so now we're going to go ahead and shift over to use cases, careers, and majors that you can go ahead and use machine learning in. So yeah, let's talk about machine learning by application. So, the uses of machine learning are really only limited by our imagination. You can use machine learning anywhere. You can use them in agriculture. You can use them anywhere you can really think of it. Because machine learning is just a tool. It's just a way to find pattern in data and make decisions based on it. But a lot of the common and interesting ones are digital assistants. So I kind of mentioned this earlier, but like Google Assistant, Siri, all these guys go ahead and use some NLP and stuff to go ahead and get good results. Secondly, recommendation. So this is actually really big for companies like Netflix, Facebook, Google. They all want to give recommendations for you. Spotify, right? For the ease of customers, so that you're not recommended random stuff that you wouldn't regularly watch. These companies go ahead and use past data to try to predict what you would like to see. Next, similar to that is contextual advertising. So, based off what you've done, what you look at, a lot of these companies want to give you ads that are relevant, ads that you'd maybe use. So based on other people and yourself, they go ahead and build these complex machine learning models which decide what ad should I give this person based on a bunch of ads. Chatbots are kind of similar to digital assistants, right? To give good feedback, to respond to questions it's never seen. NLP is a really great tool for it. Fraud protection, cybersecurity are all fields that are growing in machine learning. To have machines learn what are how to protect and how to protect against fraud and all these things. Medical imaging is actually a very interesting field where computer vision and classification is becoming very big. So you can feed in an X-ray with all these tools that you're using for medicine. You can go ahead and have machine learning models, give advice based on that. There've been a lot of advances in finding cancer cells or finding tumors simply by looking at an X-ray. So as computer vision continues to grow, these tools are going to only get stronger from this point on. And lastly are self-driving cars. So I mentioned this before, but yeah, using computer vision and image identification and a lot of other tools, even reinforcement learning, cars can learn how to drive. And that's where the future of driving is going. And yeah, now machine learning by industry. So you'd actually be surprised about how many different industries could use machine learning. So there's financial services, so you could think of stocks and a lot of other financial related items that might use machine learning for prediction. Healthcare, we kind of talked about that earlier, using machines with machine learning to get good to parse through the data. You can even think of like oil and gas or government, right? Like finding good spots for oil, that could be a machine learning problem. Retail, so this is kind of going all the way back to that example we had at the beginning. Finding demographic, something as simple as that could be a good use case for machine learning. I've seen before an app that helps you you just turn on your video camera and you look at items around the store. It'll either help you get around the store, help you identify the prices of items. So there are a lot of interesting use cases of machine learning in retail. And lastly, transportation, whether that's self-driving cars or just any other use case in transportation. There are a lot of fields where machine learning is entering. So yeah, now let's look at career options. So if you're here and you're saying, oh no, I don't want to be a software engineer, worry not. It's not just coding that's going to be needed for machine learning. So of course you can be a software engineer. And if you're a software engineer, you're usually going to do a lot of the coding, making the models, and all that stuff for the machine learning side. But there's a lot of other important roles, such as data science, right? As I mentioned, the data is extremely important for machine learning. So to come up with good machine learning ideas, to know what to do with the data scientists are very important. Linguists, so this comes in on a lot of that RNNs and NLP, right? Linguistics is kind of like the study of like the language itself, and you need to understand the language to be able to best train the models to understand that language. So linguistics is very important for NLP. And then you could be a machine learning researcher. So if you're less interested in making machine learning programs and instead more interested in advancing machine learning, you could go ahead and join machine learning research and try to improve the models that I've talked about. And you know, there's a lot of research going on, a lot of advances going on. So machine learning research is a great field right now. Data analyst, kind of similar to data science. Data is just very important in machine learning. So you know, being a data analyst is also very important. And you know, you can be a computer vision engineer focusing on computer vision, and you can even go into something like computational biology. So that has a bigger focus on biology. So, you know, if you have a better biology background, you can go ahead and try to use computers there and computation to do machine learning there. And that's just kind of like still the like machine learning coding-ish related jobs. If you want to take a step away from that, even, you know, sales, marketing, product management, business analyst, you know, all of them need to understand their product well, right? If you want to try to sell or market your product, you need to know about the machine learning that goes on behind it. Why machine learning is better than other, you know, non-machine learning models, and you need to go ahead and sell it. And yeah, similarly, business analysts, you know, you need to understand machine learning to go ahead and analyze, you know, business moves and everything based on that. There's also robot scientists, you know, which have to do a little bit more with robots. And again, machine learning is huge with the robots as well, especially reinforcement learning. Lastly, fields that you might not even think about, but are actually growing related to machine learning. You know, public policy, journalism, ethicists, and the military. So, you know, going forward, especially when things like self-driving cars are out, we're going to run into a lot of ethical problems, right? If a car needs to either run off a cliff, right, or run into a few pedestrians that are in the way, what decision does the car make, right? What's the legal decision it's supposed to make? So there's a lot of stuff that comes into taking decisions that previously humans made and now giving it to machines. And ethicists, public policy are going to be very important for that. You know, journalism is also going to be important to report on these cases, report on the growth of machine learning, talk about these ethical dilemmas in ML. And lastly, the military. The military is, especially for cybersecurity, is really looking at machine learning, and you know, machine learning is becoming a big tool for them. So yeah, next we're going to talk about major options. So yeah, not just CS. So this is kind of, I've seen a lot of people take all these other fields and also, you know, do machine learning. So there's computer science, data science, AI, linguistics. So these are all just like regular majors that would go to machine learning. Data science is a little bit more data oriented. Artificial intelligence is actually rather new. I think maybe only CMU and a few other schools offer it, but I'm sure more and more schools will go ahead and start offering it. The next step is if you want to go a little bit more on the mathy side. There's stats, maths, applied maths, cognitive science. I'm actually taking a logic minor myself, which is kind of more the philosophy of computer science. And just all these other fields like biology, human-computer interaction, these are all important. You can go ahead and apply machine learning to these because machine learning is just a tool. And lastly, you can get a domain-specific degree. You can get physical sciences, agriculture, chemical engineering. All these cases, all these like fields have a place where you can apply machine learning. All right, so next I'm going to go ahead and show you a demo. So I kind of mentioned that there was that mentee that I worked with on that project about you know, paying attention on Zoom. So I'll go ahead and play that demo right now so we can go ahead and watch that. Yeah, I think I need to escape this.
Of my code for attentive versus non-attentive students. So what I'll be doing is I'll be going through my code, and then at the end I'll be going through examples of my code running and what it's good at and what it's not good at. So At the start, what we need is to import the libraries. And what we're doing here is we're gathering the tools we're going to use. Now, the second step is collecting the images from my desktop and separating them into testing, training, or attentive or distracted students. Now, for the next one here, we're creating the model. We'll be using a lot of tools from TensorFlow and different areas. Now, for the fourth one, we actually train and we test it. So here we've done 19 epochs, which means we go through it 19 times. The biggest numbers we look for are the accuracy and the validation accuracy. Accuracy is the accuracy our code has on the training data, and validation accuracy is the accuracy our code has on the testing data, which is over here. Then our next step, which isn't really necessary, this allows us to run our code on specific images. So the function of predict image, and we're going to be using that. So predict image on ATT. So we look at this image. So what happens here is the image gets readjusted and resized for something that the model can read or something better for the model. And here it labeled it as attentive, which is correct. So our model got this correct. Now we run through the next one, same thing, our model gets it correct. And the third one, again, our model gets it correct. What the model is really good for in attentive ones is a person smiling. So if a person is smiling, our model tends to label it as attentive, and eye contact. If a person is making eye contact with the camera, the model again labels it as attentive. Now, our model is pretty good at someone who's not looking into the camera at all and not smiling. Also, the model is really good at pictures without the person in it at all, or cameras which are turned off, which is pretty obvious why it's good at. Now, the part where the model tends to struggle, from my experience of practicing or running images through the predict image, is pictures where the person is not looking directly at the camera, but they're distracted. So their eyes are in the frames, but they're looking elsewhere. Or if they're smiling, but they're smiling at their phone or something else and not looking at the camera, again, the model may mark those as attentive instead of unattentive. All these tests that you've just seen, plus the final accuracy, was the accuracy of my final prototype and my final model. I had around 3 prototypes. In the first prototype, the accuracy was around 60 to 68%. And its biggest problem was its collection of data. It lacked images. So what I did is I collected 250 images of attentive and unattentive, and around 150 testing images. And once I got this, it went up to 74, 76%. And then I started doing optimizations, and I did some various ones. And using that, the accuracy level hit around 81%. Thank you so much for listening.
All right, awesome. So that was the demo. Also, quick note, by the way, for questions, don't worry. I will go ahead and have like a small Q&A after this is done, so I'll answer all the questions there. Yeah, but
Hi.
for now, what I will do
My name is Rahel.
is I'll go ahead and so yeah, I'll just discuss a few things that you might have seen in here. So first of all, remember those libraries I talked about? Well, here is where this mentee went ahead and implemented them. So TensorFlow, NumPy, Keras, these are all things that we talked about. Yeah, there's more Keras. There's Matplotlib, which was we talked about as an option for data processing, right? So these are all just libraries that he imported. I kind of mentioned this before, but we want to have a lot of data, right? So there's, as he mentioned, there's train data and there's test data. So train data is what he's training his model on. And what you want to do is you want to have separate train and test data. And you could think of this as like the same reason for why you have separate homework and test for a class, right? They give you homework to learn the material, and then they give a separate test for you to see if you actually understood the material, right? If I give you the same test as a homework problem, then it wouldn't make any sense, right? In theory, if you just memorize your homework, you'll do great. So for the same reasons here, we keep a separate test data set than our trained data set so that we can actually tell if our model learned or not. And we make sure it's not just memorizing all the trained data set images and saying, oh, is this in the trained data set? Like, yes, if not, it's like wrong. Yeah, so that's why he had that. The next step here is kind of the model that I talked about. So if you see this conv2D thing, that's actually a CNN. So that's, we talked about computer vision or image identification. So he's doing that right now, and he's using the CNN here, which again, remember I told you, Keras will take care of that. He doesn't need to do anything. Keras.layers just needs to add a few layers, and voila, here's a machine learning model. And lastly, right here. So this slide's very interesting in that, remember we talked about gradient descent and the loss function? Well, this is how you actually use them. So here, when you do your model.compile or set up your model, you go ahead and add a loss function. So again, you don't have to create these loss functions from scratch. There are already some common ones that are used. So when you have two items, two images that you want to identify between, you usually use something called binary cross entropy. So you just set that as your loss function. And for gradient descent, there's this thing called an optimizer. And Atom Optimizer in particular uses gradient descent inside of it. On top of it, it uses a few additional things to help gradient descent do better. But it basically is our gradient descent step to go ahead and solve, find that minimum for that binary cross entropy loss function. So yeah, as he mentioned, there's going to be, he runs it for multiple steps, which are called epochs for training. And you can see that every step we get lower loss, right? Lower loss is good. Our loss is decreasing. And our accuracy is, in theory, going up. If you notice, sometimes we get an accuracy of 1, even though our, he said our test accuracy is not 1, but our train accuracy is 1. And that's sometimes what happens in machine learning. The model, the data that it sees, it knows, it learns really well. But like the data it hasn't seen, it doesn't do as well. And sometimes that's a problem that we actually need to fix. So yeah, that's kind of an overview of like a project that's, that's been done by a mentee that I worked with. So now, continuing with the presentation, I'll talk a little bit about, the program that we're hosting this fall.
Hi, my name is.
So the fall program. So yeah, the dates as of now are going to be September 10 to December 3. It's going to be a full course. So that's what the full course, if you want to learn about machine learning through, slides and labs and all that stuff. If you want to just join on the project section, if you already have machine learning background, you can join October 15th to December 3rd. So, these are all the times, the duration. And the important thing is go to eldridgeacademy.com. If you want more information, I can go ahead and drop that in the chat at the end, and email info@eldridgeacademy if you have any questions. But yeah, go to the website to see more information. So why enroll? So the idea of this course and what we achieved last summer when we ran this course was a lot of stuff, a lot of classes right now that are available for machine learning, just kind of give you a rundown of machine learning and maybe a high level overview. But our goal is more to help you build a project. So we'll teach you machine learning to the effect of letting you build your own project and giving you the ability to build projects, in any field that you want, in CNNs, or sorry, computer vision, in natural language processing, even in reinforcement learning. So what we had last semester was we split into multiple groups. Each group created a full-on project that was actually very successful. They all created posters, and we published a paper where, again, it's all on the website. So I would recommend go to the website, look at the paper, look at the presentations. They're all really great. And yeah, so the goal is to be able to take these projects, take them to a science fair or take them to a hackathon, perform well with that. And yeah, so there'll also be like a LinkedIn badge and a letter of recommendation for programmers going forward. So these are all, great perks of the class. And again, our aim here is really just kind of project oriented. Yeah, so this is kind of, as I mentioned before, success from the 2021 class. There are a lot of projects such as the one that we talked about, detecting distracted students. There was a COVID radiograph classification. So what that did is given I think this one on the top right, I'm not sure if you can see these x-rays, given these x-rays and radiographs, they detected whether people had COVID or not. So that was actually a very interesting project and they performed well. Again, I would recommend looking at their poster or their paper if you're interested for more. There was one for waste classification. So again, the problem here was, people were not recycling and throwing things in the compost or garbage correctly, and it caused a major effect. So they were able to take images and identify whether it was recyclable, compostable, or garbage. And again, it worked really well. Lastly, they had a heart attack predictor. So this is something that, would maybe work very well with an app, like, with a watch that's able to keep track of your heart rate. So it took in a variety of factors like, heart rate and a few other things, and it was able to predict whether a person, was prone to getting a heart attack or not. So again, all these papers are on the website, and a lot of these students have submitted to science fairs for this for this round. So we'll see how well it performs. But yeah, we're still awaiting those results. And overall, it was a great success. The posters, the results were all great. The papers look really nice. So yeah, so that's like the course. Again, I'll post in the chat for anything, but at this point, I'll open up for any questions. So yeah, go ahead, feel free to put in the chat, put in the Q&A, or raise your hand if you want to answer, if you have any questions. So the first question I see is, are there careers in video game industries that could impact machine learning? And I would say yes, of course, for sure. Actually, if you think about it, a lot of the AI, a lot of like the, like NPCs or CPUs, right? Like the ways they act, how they learn to act, right? A lot of the enemies that you fight, right? There's a big move to artificial intelligence and machine learning to go ahead and start making those more complex and make them react better, so that you can have a more interesting experience. So I think the video game, there's a lot of places in the video game industry that you can go ahead and start applying machine learning for sure. So yeah, feel free to add anything in the chat or the Q&A, and I can go ahead and answer any questions there. And if you don't have any questions, feel free to leave at this point. And thank you for coming. I'll also go ahead and post the link for the website. All right, so yeah, I shared the link. Yeah, continue to ask any questions. Feel free to ask any questions you have. Yeah, I think at this point we can wrap up the seminar. So, feel free to go ahead and leave. Thank you so much for coming. And yeah, if you have any individual questions, I guess you can stick around. I'll stick around till 12. But yeah, thank you so much for coming. All right, I'll go ahead and end the call.